world does a boat float?
How in the world does a light bulb work?
How in the world does a bird fly? Where in the world is the deepest spot in the ocean? Why in the world is the sky blue? Where in the world are the 7 ancient wonders?
Where in the world are the northern lights?
How in the world does the moon affect the tides?
How in the world does an electoral college work?
How in the world do bits and bytes work on the computer? How in the world do fish breathe? How in the world does a bridge work?
Hey there, fellow adventurers and inquisitive ones. Welcome aboard the airship Curiosity. I'm Pilot Lindy, and my companions and I are ready to take you around the world to show you how in the world. And you don't have to leave home to do so. You have questions, and we know just where to find the answers. So, where do we start? I wonder what it would take to get an alarm repair person up here. Just a simple ding-ding would be nice. But more importantly, that means it's time for our first question of our flight.
How in the world are clouds formed, and what are the different types?
A question that touches us way up here. Clouds, fluffy and light, sometimes like giant cotton balls in the sky. But they don't just appear. Let's get right to the explanation. In order to clear the fog on this question, we've come to a place where they don't make the clouds, but they certainly can forecast when they might appear. The National Weather Service Center in Wakefield, Virginia, is one of 125 forecasting offices in the U.S. and territories. They track changing weather, produce forecasts, and issue warnings about storms to heat advisories. It's also a good place to find out about clouds.
A cloud, in the most basic terms, is a way that one can see moisture in the atmosphere. It's the atmosphere's sort of way of being able to show that there is moisture there.
There's always moisture in the atmosphere, and once it becomes saturated, or has all the moisture it can hold, the moisture becomes visible in the form of a cloud. The atmosphere is a gaseous mass that surrounds a celestial body, especially like the one that surrounds Earth. When we think of atmosphere, we think of the air that we breathe. See? The blue sky, or clouds in the sky.
It's actually what covers the Earth. It's the air that covers the Earth, and it's in different layers. We live in the lowest layer, called the troposphere. And that's where all the weather really occurs, and the things that are really important to us in terms of temperature, rainfall, snowfall, wind, all of that stuff occurs in the troposphere.
Clouds are formed for a number of reasons, rising air being one of the main ones. We think of horizontal moving air as wind, but in reality,
there is an awful lot of motion in the atmosphere that's up and down. And it's that upward motion in the atmosphere that ultimately allows air to cool sufficiently that you get clouds to form.
All of that air movement results in 4 basic types of clouds.
There are stratus clouds, and strata meaning layer. There's cumulus clouds, which are kind of the puffy cotton ball type clouds that we often see during fair weather days. And then the third type is cirrus clouds. And cirrus clouds are made up of ice crystals. Most of the time they're kind of thin, wispy clouds, but they can occur in sort of a sheet or a layer that at times can be useful to getting a sense of whether or not rain or snow might be possible in the next day or so.
The fourth is nimbus, or rain clouds. Though all can provide moisture in the form of rain or snow, the 2 most likely are the stratus and cumulus clouds. Cirrus can provide moisture, but they are so high up it doesn't make it to ground. So let's examine the precipitation process. Remember, clouds are formed from water droplets that cool as the air rises. When enough of the droplets get together, they form clouds. If the clouds are big enough and have enough water droplets, the droplets bang together and form even bigger drops. When the drops get heavy, they fall because of gravity, and you see and feel rain.
So there are big, large-scale cloud to rain, cloud to snow processes that go on. The process that's more local in a lot of cases is the thunderstorm process. And that's the one that generally speaking is smaller scale, can occur within, for example, a city like Virginia Beach or part of a city like Norfolk, occur over a small area, or in the case of a line of thunderstorms, can actually occur over hundreds of miles in length. But the process for that individual thunderstorm is relatively small.
So how fast do raindrops fall? Well, not including wind-driven rain. Raindrops fall between 7 and 18 miles per hour in still air. The range and speed depends on the size of the raindrop. Can they fall faster? Nope. Air friction breaks them up when they exceed 18 miles per hour. So I hope that clears up a cloudy picture for you. Well, now that was a very interesting sound. What can we be curious about now?
How in the world does electricity work?
Okay, despite what you have learned, Benjamin Franklin did not invent electricity. It did not begin when he flew his kite during a thunderstorm or when light bulbs were installed in houses around the world. The truth is that electricity has always been around because it naturally exists in the world. For instance, lightning is simply a flow of electrons between the ground and the clouds. So think of those electrons flowing along wires. Let's charge up an explanation. The Children's Museum of Virginia in Portsmouth is the state's largest hands-on interactive experience for youngsters in the state. It may be the only museum where you can come and touch things. At other museums, you have to walk around and keep your hands in your pockets. Here they say, go up, touch it, play with it, push it, figure out what makes it work. And making it work is just what they will explain.
Today we're going to talk about how current electricity works. Current electricity is the movement of electrons through a circuit. To make a circuit, you need three things. First, you need something to power, like a light bulb or a DS, a Nintendo DS. And you also need a pathway. You need something to send those electrons down. Those pathways are called wires, and they have to be a conductor. A conductor allows electricity to pass through it freely, so we want those electrons to move quickly down those wires to what we want to power. And the third thing we need is an energy source, something like solar power, water power, or even nuclear power. And we have a simple machine here, and this is a hand crank generator, and Emily's going to help me out. We have something to power this light bulb right here. We have two wires. Those are our pathways to send those electrons down to our light bulb. And Emily is actually going to be our energy source. And Emily's slowly going to push electrons down. And as you can see, the light bulb barely is lit. And if Emily pushes a lot of electrons down, we see the light bulb very bright. Thanks, Em. To make this circuit work, we're going to see an open circuit and a closed circuit, and which one is more effective, and maybe how this light bulb is lit. So we're going to start with something to power, and just like with our hand crank generator, we're going to have a light bulb. And Christine, you are going to be our light bulb, so come on right here. And Janessa, you are going to be a AA battery. And to get the electrons that our battery is going to push towards our light bulb, we need a pathway. So we have this rope that we're going to pretend is a big copper wire. And I'm just going to lay it down. And Janessa, if you could put your left foot on there, that's the negative side of you. That's your negative side on the battery. And you're going to put your right foot on there. This pathway is a one-way pathway. This is direct current. So you are only pushing electrons that way. And since our light bulb has no pathway anywhere else, once the electrons come to our light bulb, then you're going to drop them because you have nowhere else to send them. Here are our electrons. And Janessa, you're a AA battery, which means you don't have an infinite amount of power. Our AA battery is only getting 2 electrons, and once she is out, our battery is dead. So battery, when you're ready, start pushing those electrons down to our light bulb. Now our light bulb immediately drops the electrons, and the only time she is on is that split second she's holding it. And if we were actually looking at this open circuit and we were looking at that light bulb, we would not see any light coming from it. To make our circuit work so that our electrons are continuously flowing, because remember, current electricity is moving electrons, what we need to do is we need to give them another pathway. We need to give our electrons a pathway going this way, and then we need our light bulb to throw electrons back to our battery. So what we're going to do is we're going to close this circuit and make it look like a big circle. Janessa is going to have the wire under both feet, and so, excuse me, our battery is going to have the wire under both sides, and our light bulb is going to have a wire going through both sides, and here is our electron. Now you can toss it, and you can catch it, and you can toss it, and you can catch it. So battery throw, light bulb throw. Battery throw, light bulb throw. And now we see our electrons are flowing back and forth continuously. This is current electricity. If we were looking at a circuit and we saw the light bulb lit, we would know that this is a closed circuit because we can see the light bulb being lit. We can see that the electrons are flowing through it continuously. We're going to look at the electrons in a little bit of a different way. We're going to see how this closed circuit, since it's just a one-way path, we're going to call this a series circuit. A series circuit is a closed circuit that just has that simple circle path. And we're going to see how the electrons flow through it, but also a major problem with it. Our battery is still here, our light bulb is still here, but now these electrons are going to go around our circle. So go on, and the battery is pushing you to that light bulb. The electrons are flowing through it, and they're moving just like the ball was moving through the air between our battery and our light bulb. The big problem with this closed series circuit is if there's a break in the wire, I have broken the wire, look what happens. Our electrons have to stop. The whole point of current electricity is that electrons keep moving and they've stopped. So to circumvent this problem, we're going to turn this series circuit into a parallel circuit. So I'm going to get a few more pathways. I'm just going to give these electrons somewhere else to go in case there's a break in the line. So I just have a wire going across, two wires going across, and ladies, go ahead and get started. And this time I'm going to put the break in the exact same spot. I'm going to stand right here, but look what happens. They have another pathway to go on. It may be smaller, but they are continuing to move. I can put a break right here, and they still have a pathway. And they can continue moving. So the question is your house wired in a series circuit where if one light bulb goes out, they all go out? Or is your house wired in parallel circuits where if one light goes out, the rest of the lights stay on? Probably your house is wired in a parallel circuit. That's why when you're changing one light bulb, the rest of the light bulbs are still on in your house.
Guess what? Electricity travels at the speed of light, more than 186,000 miles per second. And now let's see how you can generate electricity on your own.
And now, another How in the World brain game.
Today we'll answer the question, how does electricity create a magnet? We've all seen one of these simple magnets that come in all shapes and sizes. This is a horseshoe magnet. These are very common. You can take a magnet and hold it close to something metal, and the magnet will pick them up. Pretty simple, huh? Well, what if you did the same thing with a nail or a screw? Not much happens. Don't give up. What if we wrap the wire around the screw? Wrap it in one direction 30 or more times, and make sure you leave the two ends out, so it looks like this. Wrapping the wire around the screw doesn't work either. It's just not picking up the paper clips. Let's add something else. What if I add a battery and connect the ends of the wire I wrapped around the nail? What do we have? A magnet. Quick, let's see that again in slow motion. Just by adding electricity, a simple nail and wire becomes a magnet. So how does that happen? A simple nail, a simple wire, and a little electricity becomes a magnet. What's happening? If you take any piece of wire and run electricity through it, the electricity will create a magnetic field around that wire, like a tube of magnetism. So if you wrap a wire around a nail or piece of metal, all those tubes of magnetism overlap, and they line up along the length of the nail that creates a strong magnetic field. Now remember, I mentioned Ben Franklin. He did not invent electricity, but his extensive electricity research in the 18th century led him to inventing the lightning rod. Lightning rods protect buildings in the event of lightning by conducting lightning strikes through a grounded wire. Well, if the electricity was out, then that would be silent, but we would miss another great question.
What in the world is a sweet spot on a baseball bat?
Popcorn and peanuts and the crack of the bat. Can anything represent spring and summer more than baseball? A simple game. You throw the ball, you catch the ball, you hit the ball. But hitting the ball is more than just swinging a wooden stick at a round ball. There is science involved. To swing for the fences on this question, the airship Curiosity didn't show up at the ballpark. We're at the Jefferson Lab in Newport News, Virginia. Jefferson Lab is a basic research laboratory built to probe the nucleus of the atom to learn more about the structure of matter. It also is a cool place to learn about the physics of baseball and the sweet spot.
Okay, well, the sweet spot is actually a term that's used more often than it's defined. I mean, it could have multiple definitions. And so when I refer to the sweet spot, normally I'm talking about the best place along the barrel of the bat to hit the ball in terms of what will make the ball come off the bat fastest.
When you hit a ball just right, you've hit it on one of the two sweet spots of the bat. One of these sweet spots relates to vibration. Whenever an object is struck, it vibrates in response. These vibrations travel in waves up and down the length of the object. At one point, those waves cancel each other out. That is the node. A node is a spot along a standing wave where the wave has minimal movement. Take a look at this drawing. See near the top of the bat where the red line and blue line are closest together? These are nodes, and that is where the vibrations are least when the ball hits the bat.
Everyone who has played the game enough knows that when the ball doesn't hit the bat on the sweet spot, it stings your hands. And what does that mean, sting your hands? It means that the collision is exciting vibrations in the bat.
Vibrations occur in all bats, aluminum and wooden. You feel it more in wooden bats because they are made of a solid piece of wood, following a process that has existed a long time. Hillerich and Bradsby have been making the famous Louisville Slugger bat since the 1880s. While ash is the predominant wood used, birch and maple are also employed. After the trees are cut in the forest and branches trimmed, the trunks are then cut into sections and shipped to mills. A worker will arrange these pieces on a mechanical lathe that turns the wood as it shaves off all the rough edges. The remaining piece is known as a billet. The billets are stored in a place to dry out from moisture and sap. The billet is then put on a lathe, which shaves off any excess wood until the shape of a baseball bat emerges from the original piece. It now closely resembles the finished product in terms of its shape, with a narrow end that is the handle and a thicker end that will be the barrel of the bat. These are sanded and undergo yet another inspection before they are separated according to their weight. The trademark is branded on the bat, and then it gets a bath and stain and a coat of varnish. Then it is ready to hit. So, where is the sweet spot?
You could just take this bat and tap it ever so lightly with the ball at different spots, and you find there's a spot like right here where the vibrations sound really very different. They're much higher frequency vibrations, and that's essentially the sweet spot. This is where that sweet spot is, and it's pretty reproducible. And that's very typical. You know, it typically appears somewhere between 5 and 6 inches from the end of the bat, and you know, virtually the same for all bats. I mean, all bats more or less look alike.
So what happens on contact?
When the ball hits the bat, a wave is created that bounces down to the end of the bat, bounces back, and eventually just bounces back and forth a bunch of times. That takes some time for it to get down there and back again. And by the time the reflected wave gets back again, the ball has already left the bat.
When the ball collides with the bat at a node or sweet spot, the bat vibrates less, and so less energy is lost into the bat from a collision of the ball and the bat. With more energy, the ball travels further.
Now, fortunately, in terms of the definition, you know, the various possible definitions of where the sweet spot is, like where you get the biggest bounce off the bat, where it is the batted ball speed the highest, where are the vibrations minimized, they're all about at the same point. You know, that's typically at a point maybe 5 or 6 inches in from the tip of the bat. And really, from the point of view of hitting the ball and, you know, making the vibrations go away and getting the highest batted ball speed, there is one point that is the best point, but really anywhere within, you know, maybe a 2-inch band would equally suffice.
From the forest to the baseball field, a wooden bat takes several years to produce. Lumber must be dried and seasoned for 6 months to 2 years before being made into a bat. Once it reaches the field, the average lifespan of a major league bat is just 1 month. And with that, it's time to swing out of here. So until the next time, keep looking up for the airship Curiosity. When you see us, maybe we'll have an answer or two for you. You know, cool stuff like, how in the world can squirrels fly? What in the world makes super glue so strong? How in the world does radar work?